Good morning, we are Group 4, and in this presentation we will be showing our analysis for week 1 of the refrigeration lab. Refrigeration is used in heat pumps often to transfer heat from a source to a sink. For this lab, we are modeling, analyzing, and characterizing a refrigeration system that uses air instead of refrigerant. This slide shows the system diagram and setup of the experiment. As shown by the orange line with arrows, compressed air at T1 goes through a thermocouple, enters a heat exchanger, and then an accumulator. This week, since both the incoming airstream and the ambient air are at the same temperature, the heat exchanger is effectively ignored. So, the air then enters the vortex tube with temperature T3 and pressure P3. The vortex tube divides the airflow into a hot and cold stream. The hot output at T4H and P4H goes through a flow sensor where we obtain m.hot. On the other hand, the cold output at T4C and P4C goes into the insulated aluminum load, exits at temperature T5 and pressure P5, and goes through a flow sensor where we obtain m.cold. The goals of this week's lab are to characterize the vortex tube's steady-state behavior and the relationships between P3, T4 hot and cold, and m. hot and cold. Also in this experiment, we determined the time response, the effective mass of the load, and the thermal resistance of the block at 50 and at 80 psi.
Here you can see the plots of temperature versus time and pressure versus time for the vortex tubes. First, we took the raw data from the thermocouples and found offset values to correct the starting temp of all thermocouples to room temperature. This method is of course operating under the assumption that all thermocouples were actually at room temp at the start of the experiment. After correcting the thermocouple data, we used these plots to identify the steady-state regions denoted by the horizontal brackets on the temperature versus time graph and the horizontal blue regions in the pressure versus time graph. After identifying the regions, we segmented the data and averaged the value to remove noise and get a more accurate answer. Here you can see the results of this process for the steady-state behavior of the system as the pressure P3 varies. We have a high degree of confidence in these values since we found the offsets to zero the thermocouples to room temperature and then used averaging to remove noise from the data for these values. This data is the precursor used to experimentally determine and characterize the relationships between P3 and other variables shown. As P3 increases, the T4C value decreases. T4H and V dot values show an increasing trend. These were the relationships we found between P3 and T4 hot and T4 cold. These relationships were found by plotting pressure and temperature on a logarithmic scale and finding the York regression of this data. The relationships seen make intuitive sense. As the pressure, and consequently the mass flow rate, of the vortex tube increases, the delta between the hot and cold gas increases. This is a logarithmic relationship in reality, but by plotting on a log scale, we can see a clean linear relationship. We have high confidence in these results based on the low slope and intercept uncertainties that are derived from the relatively low uncertainties of the instruments used. Similarly, here are the relationships between P3 and the hot and cold mass flow rate, along with the uncertainty analysis for this regression. Again, the relationship seen makes intuitive sense. As the pressure increases, so does the mass flow rate of the system for both hot and cold gas. Notice as well that our uncertainties for this regression are higher than the previous slide. This is because as we use more sensors to collect data and calculate a value, the error propagation causes a higher uncertainty. In this case, the calculation for mass flow rate used both an ambient pressure gauge, thermocouples, and volumetric flow sensors. If we had more accurate and precise sensors, we could have a higher degree of confidence in our answers for these calculated values.
Moreover, the theoretical thermal resistance of the block for both 50 psi and 80 psi was calculated to be 29.65 Kelvin per watt. It was found using the equation shown on the screen, where L is the thickness, A is the surface area, and K is the thermal conductivity of the styrofoam at 0.033 watts per meter Kelvin. On the other hand, the experimental thermal resistance was found by equating the heat loss by the block to incoming cold air stream by convection, or Q dot air, to the heat gained by block from the ambient air by convection, or Q dot ambient. At steady state, these two values, Q dot ambient and Q dot air, are equal to one another. So, the experimental thermal resistance is T block, which is temperature of the block, minus ambient temperature, over the cold mass flow rate times specific heat times the cold T4 minus T5. This resulted in a thermal resistance of 4.57 Kelvin per watt for 50 psi and 3.018 Kelvin per watt for 80 psi. As you can see, the experimental values are wildly different from the theoretical values Theory predicts that insulation should be more effective than it is. One reason for this is that we are implicitly assuming in this calculation there is no heat loss along the tubes or in other parts of the system. In reality, these are uninsulated and are a contributing source to heat loss. Consequently, we find experimentally that the R value of the insulation is in fact lower than theory.
On this slide is the time response analysis for 50 psi on the left and 80 psi on the right. These were found by doing a York fit on the plotted data of time versus the log of the block temperature at set time minus the block temperature at steady state. This provides us with the values for tau and beta, which was extracted based on the natural log of the York intercept for beta and the negative inverse of the slope for tau. The uncertainty involved are small for tau and significant for beta values. These values can then be used to determine the length of the transient response of the load, which will then be used in the mass calculations. The effective mass of the load was obtained by analysis in the transient condition. The effective mass of the load was found by equating the heat lost by the block through convection or Q dot air to the energy rate change of the block or Q dot mass. So the effective mass of the load is calculated using the formula shown. This resulted in a calculated mass of 552 grams for 50 psi and 845 grams for 80 psi versus a measured mass of 454.3 grams. Again, the experimental mass is much different than the measured mass. Since the error from the York fit was relatively low even after EPA, we can conclude that the large discrepancy in our results can be attributed more to the assumptions made in our theoretical calculation, like the range of transient response, rather than instrument uncertainty, though it is also a partially contributing factor. In conclusion, through the lab, we characterized the relationship between P3 and the output temperatures and flow rates at both ends of the vortex tube, calculated the thermal resistance of the insulator, and experimentally determined the mass of the block. One observation from all the experiments conducted are the presence of errors that arise from theoretical assumptions made during calculations, as well as errors that arise from the use of sensors. The relationships found using a single sensor reading are more accurate than calculated values which are found using multiple sensors. The EPA shows us that we have lower confidence in these values when more sensors are involved. That being said, the results of the experiment make sense and provides us with insight into the overall functioning of the system. Once the errors were accounted for, this understanding will be used to guide the analysis in the final lab. These are our references. By this, we conclude our presentation. Thank you.